Hi everybody, and welcome to my presentation on why voice coils burn out, or rather, why I think voice coils burn out. The leading cause, in my opinion, is poor ventilation of the voice coil. Anyone who has ever had a voice coil burnout knows that that's a real disappointment. But when you look at the structure, it's such a tightly confined little spot for the voice coil, there's very little air that can move in there. Well, I burned one out, and so I dissected my loudspeaker and discovered what I believe is an underlying problem of a weak permanent magnet field. When you have a weak field, you tend to have lower output, and what do? Typically, you turn up your volume, so you overdrive a little bit. Well, that compounds your problem of poor ventilation because that heats the voice coil up even further. Before I get into my explanation, I'd like to go over basic motor operation, just so we're kind of on the same page. I'll let you read that information on basic motor magnetics, but let me explain the drawing. The green circuit here is the variable field circuit, which is driven by your audio amplifier. And in the voice coil, we produce these magnetic field lines in green, excuse me, that I've showed you here. We also have a permanent magnet circuit showed in red, which is essentially a permanent magnet, which a connection to a structure that forms a gap where we have this arrangement of magnetic fields. This 90-degree relationship is important. The other important thing of this drawing is that this electrical circuit is powered by wire. It's electrical, so we use wire to get the energy to create this field. So that goes to the voice coil. That's the voice coil. In the fixed field, the permanent magnet has to be connected mechanically, and we use a permeable metal to connect those together, and I'll show you exactly what I mean. This is the magnet on the back of a woofer. The large gray structure in the middle is a ring magnet. The two shiny structures on either side of that are the permeable metal attachments. And we're going to cut this right down the middle in a drawing and show you the insides. This is a basic drawing of how the fields work. In the first example here, shown in red is our permanent magnet field, and heavy lines mean heavy field. The green lines going also heavy, going in a 90-degree direction, are our variable field lines. In this case, both fields are equal and they're very strong, and the result shown with this black arrow is a large mechanical output. So this is maximum output right here. Let's say we turn the volume down, which that does. What that does is reduces our variable field, the green flux lines here, but the permanent field lines are still the same because nothing has changed with the permanent magnet. The resulting mechanical force, though, is lower because the variable field is lower. In this example, we have a fairly low permanent magnet field, and we've turned up our variable field to compensate. But since this is a weak field, our output stays low as if it was turned down, as in this example. This is the drawing of the sliced open magnet that I wanted to show you, and what we're going to look at is the field path. We are trying to energize this gap right here. It's circular, of course. So if we look at the path for the north magnetic field, it kind of runs along the permeable material like that, ending at the gap. And the south side, we also want to form that, get that field up there, but we have to go quite a distance here to get to the south side. And of course, this repeats over here. And that's again to form this gap here where this voice coil rides in and out, and it's a very, very close tolerance. As we look at this, we see one thing that kind of stands out. One, the path lengths are quite different. And while this doesn't look like a large distance mechanically, in terms of magnetic flux, this is quite a impedance to getting that flux energy from the South Pole up here. In fact, we estimate that the gap strength is reduced by about 40% due to this extra length of this south path. So the South Pole is weaker, and of course in a magnetic circuit, the weakest link determines the strength of the whole magnetic path in this case. The South Pole flux path takes a 90-degree turn, which is not that much as by itself, but it does extend the length. And reluctance, you can look up reluctance, which is what happens when you have excessively long permeable paths. So in summary, of the classical design, the north and south flux paths are unequally long, unequal length. That's an unbalanced condition. Gap flux is therefore limited since the total magnetic circuit is weakened by the south flux path. There's a few alternatives. One that I can't help suggesting is the moving magnet instead of the moving coil. Would you believe a magnet that big could produce the same output as a magnet this big? Check out the moving magnet subwoofer, and you can see what you can do with a 3-ounce magnet instead of a 6-pound magnet. You could also re-engineer the South Pole permeable structure of your conventional or classical speaker to lower the reluctance. You can also add more magnets. Adding more magnets simply makes the path longer. So, and you can also install thermal protection to protect your voice coil if you'd like to go that way. Thanks for listening.